Hi, Cecile. How are you?
Yeah, I'm fine, thank you. How are you?
Yeah, I'm doing great. Excited to hear from Professor Vlatko today. Hi, Professor. Welcome to the room.
Thank you very much for inviting me. It's a great pleasure. I've got Chiara Maletto next to me as well, actually.
Hello, everyone. Nice to be here.
Yeah, and welcome to Quantum Photonics, Professor Vlatko and Chiara.
Thank you.
Thank you.
We are excited to hear about your paper.
Thank you. Actually, thank you for noticing this as well. We were very excited about that work ourselves, and we are very happy to talk to you about it.
Yes, so Chiara, are we pinging some more people in? Please wait for a while so that we'll get more people to come.
Yeah.
Yeah, thanks, Vlatko and Chiara. So it's a very much pleasure to meet you here and have you join this session. So a little bit hands up. Our format today will be like a short presentation on the talk on introduction about your research. Regarding to the spin statistics, space-time, and quantum gravity. And then we will open the floor for the that will lead us to some great fruitful thoughts. So I can appreciate your effort and time. Yeah, much look forward for the discussion today. And also welcome everyone in the room. So feel free to engage in the conversation. And we'd like to present the Professor Vlatko and Professor Chiara's work to all of you today. And thanks for listening.
Yeah, thanks a lot.
Thank you. We can just wait for you to tell us when it's a good time to start, and we can give you, as you said, a brief, maybe a very kind of simple intro into what we have been doing, and then we are happy to engage in a discussion. Actually, hopefully there will be lots of questions.
Yeah, definitely. I have like a long list of questions ready to ask you today.
It's great. Yeah.
Yeah, maybe I will do a quick introduction at the starting point. Again, so welcome everyone to join our special guest event today with Professor Vlatko and also Professor Chiara today. So at the top of the room, I pinned the article, the website about Professor Vlatko. So yeah, he's a very famous scientist and a professor in the Department of Physics at the University of Oxford, and also the Center for Quantum Technologies at the National University of Singapore. So he's well known for his research on the theory of entanglement and also the quantum information theory. So he has dedicated his life and passion to the quantum information processing and related research. So he published over 300 research papers in the quantum mechanics area. So we feel really honored today to present Professor Vlatko and his amazing research today. So welcome everyone to join us. And also along with Professor Vlatko, we are honored to also have Professor Chiara to join us too. So she is also a pioneer in the quantum field, especially she is a pioneer in the field of the constructor theory, a new theory to generalize quantum theory of information. So we also want to hear her to talk about that if we have time. So Chiara and Professor Vlatko both work at quantum information lab at the University of Oxford. So welcome everyone again to meet our special guests today. I got interested in their research basically because their novel model and normal model about spin and the statistical relation theory, and also the specific explanation about the space-time and how it's correlated to the quantum gravity. So I will give the mic to the Vlatko and Professor Chiara. So if you can give us a brief introduction about yourself and your research and how you get into the field, and especially what make you come up this specific model about the quantum gravity with the relationship with the spin statistics and space-time. That would be much appreciated. Thank you.
Thanks a lot.
Thank you.
Thanks very much for such a wonderful introduction. And maybe I will say a few words, and then probably Chiara can follow it up and correct all my mistakes as well as we go along. The main question for us really is this issue of locality, in the sense that we know that physics is really, ever since probably the days of Faraday, I guess, and Maxwell with the electromagnetic field, we know that you cannot affect things at the distance instantaneously. So whatever you do at one point has to then propagate, and we know that this propagation can at best be really at the speed of light to another point. And you cannot really change things over there by acting over here instantaneously. It always takes time for these things to propagate. So that's kind of what Chiara and I have been thinking about a great deal, because, and many of you may know this, frequently you hear things like quantum entanglement. It's really non-local. You will frequently read papers where people say quantum mechanics is non-local even. But in fact, if you look at it more carefully, then quantum mechanics is as local as any classical field theory, like the electromagnetic field. In fact, quantum mechanics, quantum field theory itself is modeled on this classical field theory, and it fully rests on all the principles of locality, causality. It takes into account, of course, relativity, and so on. And we know that nothing really can propagate faster than the speed of light. And that's kind of what Chiara and I have been thinking about for some time now. What was interesting to us is that certain effects in quantum mechanics are claimed also to be non-local, not just quantum entanglement, as I mentioned, but the well-known Aharnov bomb effect. So this is a phase that's acquired by charged particles when they move about in the electromagnetic field. And there are some models which indeed do look non-local. It looks like the charge can actually be affected by a field that only exists far away from that charge. And that also attracted our attention, because it would indeed be surprising if there was something really genuinely non-local. So Chiara and I wrote a paper about it a while back, offering a completely local model of this effect. And then we really started to think, I think this came from Chiara, and probably she can say a few more words about it. The question was, is there anything that remains out there that really is still, could be claimed to be non-local? And the interesting thing is that as we know, or let's put it this way, as far as we know so far, there are two kinds of particles in nature. They could be bosonic or fermionic. And this is how it links to spin. That kind of explains our emphasis on the spin in this latest paper that you mentioned. So basically, we know that the key feature of these particles is that if you swap two of them, you will acquire quantum mechanically a phase, if you are talking about fermions, which will basically be a pi phase shift. It's just a minus sign in front of the state of two fermions. Whereas if you do that with bosonic particles, then nothing will happen. And in fact, you can measure, I think we had various proposals how to measure these kind of fermionic phases. But the weird thing about it is that it looks as though, and I think this now is the key to this paper, it looks as though this phase is also magically acquired at a distance, because you can swap these electrons so they never actually even cross their paths, if you like. They never have to occupy the same point in space at the same instant of time. And yet, when you completed the whole evolution, you actually get this pi phase shift, the minus sign. And I think Chiara was insistent on the fact that maybe even this should be thought of locally, which then automatically, of course, suggests the idea that it could be mediated by some kind of a field, the same way that I mentioned everything else is mediated when you have a causal and local account.
Yes, and I think the interesting thing there is that I think kind of Vlatko had this nice thought that this field could be gravity. So gravity is one of the forces, let's say, that are fundamental in our universe, and it's weaker than, say, the electromagnetic forces. And it sounds like a natural candidate for being the mediator there. And I think what was very interesting when Vlatko told me about this was that then we thought that we could discuss in this paper also an interesting consequence of this model. And this consequence is that if it's true that the fermionic phase, this -1 phase, is really mediated by gravity, and there are some equations that seem to say this is consistent with what we can observe on fermions, then we can also say that because you can create entanglement through phases, we can test whether gravity is quantum by generating entanglement between two fermions. And this was a second piece of kind of exciting, of an exciting idea which we put together in that paper. And this is exciting because many people still question whether gravity should be quantum or not. So we know that there are, in a sense, really two different ways in which systems that can contain information manifest themselves. There is the classical information media, so these are like bits, and then there are the quantum information media, and there are which support quantum effects and quantum computing, etc. And some physicists still bet that gravity is a classical system, and this is of course because Einstein's equations that describe gravity are completely classical. But with this test, with this idea that we describe in the paper, we could use this interesting effect that exists between fermions, not just to show that actually these fermionic phases are quite locally, but also that if it's mediated by a field, and this field is gravity, which is a big if, then this field should be quantum, if we can observe entanglement between two fermions. And this was also very exciting to us.
Yes, and I think somehow gravity feels natural to us, because it's really the only force that as it were sees everything, in the sense that, you know, anything that has energy, and I suppose everything has energy, is somehow seen by gravity. Yeah. So if there is a universal, because of course, you know, we needed to explain this phase upon exchange for all particles, fermionic or bosonic, no matter what they really are, what kind of field they may belong to. So we thought gravity is an obvious candidate. Of course, it's not excluded that there is yet another field that would do this, and one can easily write a model for that field as well. And I think what Chiara said would also hold for that field in this case, namely that it would have to be quantum mechanical as well. You couldn't get away with a kind of semi-classical description. Maybe just one last thing to mention before we maybe can discuss this more and maybe go into questions and so on, is that what we find very interesting is that when we learn about various things in physics, you know, your undergraduate degree, even some graduate courses, you are never really exposed to the full extent of quantum mechanics and the superposition principle. For instance, even when we now say you swap two particles, there are so many kind of different ways in which you can do this quantum mechanically. For instance, you can do it in a superposed way, that in one branch of the superposition you do half of the swap, and in the other branch of the superposition you do the opposite of the swap, and you will again get a relative phase, which is basically pi phase shift if we're talking about fermions. And that kind of features in this paper as well, because you can do almost like any fraction of a swap, and you can repeat it many times to build a phase shift, which is kind of maybe an intuitive piece of evidence for us that suggests to us that maybe even this quantum statistical phase is really mediated through some field locally. So I think it's always interesting to us that whenever you look at the superposition principle, you can actually apply it creatively in many ways. And it seems that we haven't quite exhausted that, even in these well-established, or what people would consider well-established areas in quantum field theory. So we were very excited to actually think about these things.
Yes, and maybe one last point also more broadly is this fact that as we revisit some of these basic ideas, such as particle statistics, and then even, you know, the classicality of the gravitational field and so on, which is given by the fundamental equations that Einstein came up with, etc., we see that most of the stuff that's being presented in textbook is actually sometimes is a bit kind of shaky.
Yes.
So it's very interesting to us that even the Aharonov effect, for example, that's somewhat like a pillar of fundamental quantum theory that you're presented in undergraduate courses in physics. If you dig deeper, you always find some aspects of the explanations that are not quite watertight.
Yes.
And somehow this piece of work was to try to make some of these explanations, which currently are a bit not so satisfactory, to make it better and to kind of go deeper.
Yes. I think this might be a good message to young researchers as well, actually, because whenever someone senior tells you, oh, this is really well understood, it should actually be like an invitation for you to jump on this and actually try to understand it even better, because nothing is really, as we know, you can always understand it at a deeper level. And so I think that's what's interesting about this, that you can be playful even in an area that's very kind of considered established. I think that's kind of like a very brief intro, but we can say more about various aspects as well.
Yes, if you want to ask some questions, or we can go into more details if it does an interest.
Yeah.
Yeah, thanks very much for the introduction. I see the RQ flash your mic, so please go ahead with your question.
Hi, Vlatko. I would like to say Dragomir. I have a question regarding the quantum gravity research that you're doing. So, as you mentioned, like there are two types of particles, bosons and fermions, and bosons are like the energy mediating particles. So, if quantum gravity is in future, if it does appear to be correct, then is there a possibility of graviton to be added into the standard model of an elementary particle? That's my question.
I think it's a very good question, actually. As you no doubt are aware of course, this is meant to be a spin 2 particle, and the argument for this is very simple. None of these arguments, obviously, all of these arguments are physicsy arguments. You know, you can never prove something. Ultimately, you have to test it. But it's simply counting the number of degrees of freedom that you need to reproduce all the multitude of gravitational components in Einstein's general relativity. This, according to our logic, would also be subject to this. However, I have to just say that it seems to us, even this you should of course not take for granted. It seems to us that gravitons, and there are various papers written on this topic, might be extremely, extremely hard to detect. You may be able to infer their existence very indirectly in some ways, and I guess what Chiara and I have been working on could be thought of in this way, but very loosely speaking. But I think to get to that level where you're really going to be able to do a swap of two gravitons and try to confirm the phase, if you do this in this kind of quantum controlled way, this seems to me really like an almost impossible experiment. But yes, our theory would suggest that this indeed would also conform to this kind of logic of the kind of statistical phase being mediated through the gravitational field itself, which sounds interesting, as you say, because in this case gravity kind of almost plays a dual role, because it would give rise to these particles, gravitons, but they would be the mediators, which you would have to basically establish the phase, which is interesting.
Awesome. Yeah, that kind of answered my question. Thank you so much.
Great. Thanks for asking.
Yeah, thanks for the question. I also have a question, if I may. So, it's very interesting to hear you talk from the spin statistics and then come to a new theory about quantum gravity. But my question is, in my understanding, I understand what is Fermi, what is boson, and what is half integer, and with minus sign shift that will become to an integer spin. But that sounds like it's a mathematical model or mathematical construct. But how can we relate that to a deeper physical aspect, to relate that to the quantum spin, angular momentum on the interaction between particles, and further to relate that to the quantum gravity? Yeah, that's something I couldn't figure out. So but that's very intriguing, and I feel there may be some connection. So if you can guide me more, I'd be very appreciative. Thank you.
Yes, I think this is a very, very deep question that you are asking. One could argue that we still don't quite understand spin in the way that that you are also suggesting, in the sense that, yes, it's kind of part of angular momentum, but of course, one should not think of anything as really spinning. It's more like an internal, intrinsic, we would call it, intrinsic degree of freedom. But of course, even though it's an intrinsic degree of freedom, we know about it precisely because it couples to all sorts of other things and determines bulk, even properties. So in that sense, you could think maybe one nice thing to think about, as always, is the Stern-Gerlach experiment, where this spin couples to the external magnetic field, and of course, if you have a spin in a superposition of two different values, up and down spin in the external field, then obviously you get this kind of superposition of spatial trajectories. So it's in that sense that's when Chiara said that it forces us to think of gravity as quantum mechanical. It's precisely because if gravity is to couple to something that's in a superposition of states, then it must understand what it means to couple to something. It's always the kind of Schrödinger cat style experiment. So either gravity doesn't understand that, in which case presumably this wouldn't work. It would just simply collapse in some way, or gravity has to be quantum and has to get entangled, meaning that the gravitational field would have one particular state if spin is pointing in one direction, and it would have a different state if the spin is pointing in a different direction. But I think this still doesn't quite address what you were asking, in the sense, I think you were asking more, how do we understand the property of spin? It does sound very mathematical from what you are saying. We are basically thinking about it through rotations that we apply, just the usual three-dimensional rotations. And because it behaves the same way as angular momentum, we kind of think of this as part of angular momentum. In fact, you can build any angular momentum by simply adding enough spin half angular momentum. You could think of this is almost like the fundamental angular momentum, out of which everything else can be can kind of be constructed. But I think it is a kind of a more hidden degree of freedom than the ordinary maybe space, which is more visible, or as you said, rotations. Is this what you had in mind?
Yes, I think you got my question. Or maybe I can answer a different way. Is that how do you know the gravity still exists in the quantum scale? So yes, yeah. Thank you.
Yes, that is the key question, really. And I think Chiara and I have been thinking about this maybe over the last 5 years or so. I think at present, all our experiments in that domain could actually, unfortunately, still be explained with classical gravity. So even people who superposed, for instance, a neutron, there is a very famous experiment in the 70s even, I think, which did neutron interferometry, where the neutron was basically superposed across two different heights in Earth's gravitational field. And then at one height, it gains one phase. At a different height, it gains a different phase. And the interference simply gives you this phase difference, the kind of mg, the mass times the gravitational constant standard height, the difference in height. And that's what people measured. But actually, you can completely explain this classically. There was nothing really, there's nothing necessarily quantum in that experiment. And that, I think, prompted Chiara and me to think about a more complicated variant of something like this, which would actually be to take two masses and superpose two masses and let them couple through gravity only, and then wait to see whether they get entangled through the gravitational field. And this I think we think would be a much stronger piece of evidence that at least some components of gravity could not be classical. You definitely could not explain this classically. We could kind of rule out almost any semi-classical model we could think of, I think. Things like field theory in curved spaces and any collapse model, collapse would be ruled out and so on. But I think it's difficult at present with the current experiments to actually be conclusive about the quantum nature of gravity.
Thanks for the answer. Actually, I wanted to ask something related about that also,
yes.
So I wanted to ask, how would you think about, verifying, your idea, but I guess you already answer, that, in your answer. So I suppose you mean then it's very difficult to verify the idea in your paper. Then it's very difficult, and at the same time there's no clear idea yet, about how to proceed to check it or to verify the idea. That's my first question. And my second question is a more general question. I think it's really easy to get, misunderstanding, some basic misunderstanding in quantum mechanics. So I hope you can help me a bit here. So according to my understanding, quantum mechanics is really a framework, where it allows you to do, calculations. So it sets out rules, where you can do, experiment, and you can do measurement and things like that. By itself, it doesn't have the concept of local or, non-local, not local or non-local in it. And so that's why I don't understand much, when the word, local is used to describe, local or non-local is used to describe quantum mechanics. Thank you.
Great. Let me actually, maybe I think both Chiara and I have probably a lot to say about some of these things. The first point first, you are right. It's a difficult experiment. It's a challenging experiment, but I think what surprised us is that actually it looks doable, almost doable, even with the current technology. I think, within the next 5 to 10 years, I think people could think about superposing the masses of the size that we need, really. They're still small, incidentally, compared to what frequently people take as the kind of threshold, which is Planck's mass. We're talking probably about six orders of magnitude smaller, or even smaller than that, which would be enough to keep in a superposition for a little while, which to us looks doable in a way. So it is a certainly challenging experiment. However, we do have the know-how, and we probably do have the resources from quantum technologies to go in this direction. So I'm quite optimistic that at least some of these will be tested at some point.
Yes, and on this note, I think there is a lot of there's been a lot of progress in quantum metrology, and in the past maybe 10 years or so, also as a result of quantum computing, etc. So I think the scheme that we proposed is maybe doesn't narrow down the technology specifically that we will have to use, but it's specific enough to give experimentalists like a clear path, the direction in which they have to look for in order to test whether gravity is quantum or not. And I think this is a really exciting new thing, because until before this experimental scheme was proposed, there are these theoretical proposals that describe gravity as quantum, but it was very hard to imagine a way of testing them unless you went into some maybe cosmological scenario, which is extremely hard to kind of access in practice. Whereas this tabletop experiment is really accessible. So compared to this,
it doesn't have to be a kind of CERN high energy.
That's it. So
complexity.
It's kind of 3 by 3 by 3 meters, right?
Yes, that's it.
I see. So like the people in string theory, like if they somehow thought up a way to test their theory, and then if they are successful, then it's also a confirmation of the
yes, you're right. String theory in the lowest level of approximation should reproduce exactly what we are predicting, and so should any probably canonical approach to quantum gravity, whatever people have out there. There are many approaches, by the way, but string theory indeed should actually also agree with this.
Yes, and the strength of the approach that we are suggesting is that it's based on a very general argument which doesn't assume any of these specific dynamical models for gravity. So it's based on general principles, and this maybe brings us back to the second part of the question. One principle being locality, and the other principle being the interoperability of information, which is basically a principle about information theory. So these are two very, very general principles that are obeyed by most theories we know. So in that sense, we are not relying on any specific model of quantum gravity to reach our conclusions, which is important because we want to test whether gravity is quantum. We don't want to be circular and assume that we're using already a quantum model for it to reach our conclusions.
Yes.
And in regard to the other point you made, I think I think I have a different view about quantum theory, and I think that it's not simply a calculational framework. It has a very rich set of ideas about what physical reality looks like, in the same way that general relativity does. And just like general relativity, it's also very counterintuitive. So in a sense, I think initially when people tried to understand what quantum theory meant, they recoiled a little bit, and they tried to think exactly as you said, as if this was just a mathematical way to reach some kind of predictions about experiments. But actually, in the past 20, 30, or 40 years, actually, we've made a lot of progress in understanding what things like quantum superpositions and entanglement and measurements of quantum systems actually mean. And all of this makes sense, the same way that Newtonian physics makes sense. It's just it's different and requires different concepts that sometimes we can't even phrase in the classical logic. But it all kind of makes sense. And in particular, quantum theory, I think as Vlatko said earlier, is local. So in a sense that it talks about subsystems, and these subsystems are independent from each other. And when you do something on one of these, nothing at all changes in the properties of other subsystems. That's the important thing. And if it does change, it's because these two systems are connected in some way, and there is a signal going from one system to the other, just like in classical physics.
Yeah.
So in that sense, I think quantum theory is completely fine as far as locality is concerned.
Yes. Maybe I can add something to that I don't know, I hope it's not a big digression, because I think something you said was also interesting there. And the point is the following. Maybe I can say it slightly differently. That quantum mechanics, when you look at the mathematical side, you can say quantum objects live in Hilbert spaces. They live in these highly abstract vector spaces there, and then you manipulate them by, multiplying these vectors by matrices and so on. But then you have to apply it to a real physical situation, which is exactly what Chiara was talking about. Then, of course, you have to apply it to particles that exist in space, they interact in space somehow, and you're engaging all sorts of other principles. The funny thing about how we still do quantum mechanics, and I think Chiara and I both complain about this a lot as well, is that we almost, certainly when we teach it like this. We always start with a classical description, and then we have to intuitively decide which of these quantities, classical quantities, should be upgraded to quantum numbers, to quantum entities, to operators. And we put hats on them, as you know. Now, this sounds a bit funny because logically, what we should really do is start with a full quantum theory and then go in the opposite direction, because classical physics is an exponentially small subset of the quantum universe, if you like. So that's kind of logically the right thing. Start with everything quantum, if you like, and then take a special case where somehow in some limit you are classical. And yet we do it almost invariably the other way around. So I think in that case you are guided by many other things. And the question is really, could this be done differently or more efficiently or more cleanly, maybe somehow? There is a lot of interesting things to be said about this.
Actually, So I think, like, if we start, with quantum mechanics right from the beginning, then I think we run into many difficulties, because there are so many macroscopic phenomena that we, still don't know how to, explain with, whether or not it's quantum, like general relativity, for example, right? So that's why I think if we start with quantum right away, not everything macroscopic. We still don't know yet if everything we know about macroscopic, at the macroscopic scale can be, explained using quantum mechanics. That's the first thing. And the second thing is, I think the locality of quantum, when you say locality of quantum, I think you are actually referring to quantum field theory, where people combine relativity and quantum mechanics. It's only then that you have to pay attention to the concepts that special relativity brings to the side of quantum mechanics, because again I think by itself quantum mechanics is only a framework, just like Newtonian mechanics, for calculating things and then for observing things. Is a very, very general, non-sophisticated, it's weird, but it's very general. It's not very sophisticated. That's the way I understand it. And also my next question is, could you explain again two principles that you make use, that you were referring about in your paper? Like the locality and what is the other principle?
I think this is an interesting discussion, because frequently when we talk about these things, we use the same word, but we actually mean very different. And maybe that's Chiara can explain it, because this is a very particular and strong sense of locality that actually is not the relativistic locality. It certainly is related at some level, but this one is kind of more fundamental.
Yes, I think it's a kind of common misconception that that theories that are not explicitly relativistic are non-local, and I think the actually non-relativistic quantum mechanics is local. And it's very interesting because it's as if quantum theory somehow sniffed relativity, you know, as if it knew about it without actually having in it. And so you don't need quantum field theory to show that non-relativistic quantum mechanics is local. So you can demonstrate that if you have two space-like separated systems and you operate on one of them with a transformation, none of the observables of the other system is allowed to change. And this is the strong and general sense of locality that we that I was referring to earlier with when I said the principle of locality. So it's a very general notion. It is implied by the locality of general relativity and of special relativity, but it's more general than that.
Yes,
because it doesn't presuppose the existence of velocity, for example, or dynamics.
So what this doesn't tell you, of course, is how quickly the signal or this effect would travel between the two subsystems. In non-relativistic quantum mechanics, as Chiara said, this speed could be anything, really.
However, it's finite, and you can actually compute it through a thing that's called the Lieb-Robinson bound, which is a quantitative tool to calculate the speed of propagation of signals in things like spin chains in non-relativistic quantum theory.
Yeah, so it's interesting that it's local and yet, of course, not bounded by the speed of light necessarily, because that doesn't have a meaning in this theory. In fact, usually you take speed of light being infinite, right, in the non-relativistic limit. So locality not in the sense of what a field theorist would call maybe microcausality, that somehow space-like separated regions, your operators should commute or anti-commute. What we mean here is simply that actions on one subsystem cannot really change anything on another subsystem. But like I said, it doesn't tell you how quickly this action could propagate, because that you have to put in by hand through all sorts of interactions. Yeah. But in fact, it certainly tells you it's not instantaneous. I guess that's the main point.
Yeah, it's a law that refers to impossibilities.
Yeah, so that is something that doesn't exist. Like the concept itself, it doesn't exist in quantum mechanics by itself. Like as I learned from the textbook, right? I don't see those things. And I don't see those things also in Newtonian mechanics. But like what you are saying now is that in reality, in classical system or in quantum system, there is actually a speed of propagation that we have to take into account always. That's what you are saying. And
yes, I think you see that's what Chiara. Yeah, exactly. What Chiara was saying is that you have these other principles that are certainly not implied by Hilbert spaces and the concept of vectors and superpositions. They come from somewhere else, and it's true that some of them we may not understand necessarily where they even come from. They are frequently assumed because they make sense. They are kind of confirmed in all sorts of experiments. But yes, these are certainly principles that are possibly even external to quantum mechanics, and then somehow you're trying to make them comply. Yeah, sorry.
Hey,
go ahead.
Yeah, I just wanted to ask you a question on a point that you touched on earlier. So you're talking about these subsystems, and then in my point of view, I feel like they're interfacing, right? They're sharing some energy, and so with these subsystems, so you wanted to drift away from the classical approach of starting off with classical mechanics and then going into quantum, and doing it kind of the other way around, with making the whole system as a quantum field, or start off maybe with the Higgs field and then dive into the subsystems. Well, my question to you is, and taking also classical mechanics as a special case. So my question is, do we have all the subsystems covered? So my background is a computer engineer. That's what I do, and I work with circuits all the time, and I also work with machine learning and things like that, right? Deep neural networks. So when you're talking matrices and everything, you're speaking my language. So and vector spaces and and that type of stuff, right? But what I really want to know is how much did we cover? Can you give me a percentage? Is it 100% that we understand everything related to quantum, and then we can start there? Because if you're setting that foundation, then you mentioned earlier some things being vague or things that we don't know. Well, imagine me trying to explain, machine learning as a fundamental intro class, and then working backwards to, variables. That's kind of variables and how to store data in registers and things like that. So, does that make sense? My question to you is, again, how deeply do you understand the completeness of the system before?
I think it's a good point. Actually, I kind of see even two different questions there that you're asking. One is, of course, this one, whether we have a complete understanding, and I think we clearly don't, because we keep revisiting various questions, and we keep discovering more that there's certainly all sorts of open questions out there. It's also possible, and in fact, I think many people would even bet on that, that before we even clarify everything, what will happen is that we end up having a new theory of physics. So it's even possible that quantum mechanics will be superseded and becomes a special case. I mean, none of us can really imagine what this would be like, and we certainly have no experimental motivation at present, but that's one possibility. The other question, the other kind of hint I got when you were talking was that maybe it's to do with how we teach these things as well, because you alluded to the fact how you would teach, for instance, machine learning to someone. I agree that this is a very different question. That's true, in the sense that given that classical physics is more intuitive, it kind of, the way we teach quantum mechanics is maybe natural. I was kind of critical of that, but I was critical more in the sense of how we do it once we do it as professionals, rather than how we teach it. Maybe how we teach some aspects is necessary to do it through classical physics, but somehow when we try to explain things, I think it seems more natural to write down the full quantum description first, whatever this may mean, and then maybe take approximations and go into special cases. But I would certainly say we are still exploring various aspects of quantum mechanics, and there is a lot more to understand, no doubt.
Yeah, maybe to just add to what you said, I think the physics community sometimes makes this. It's kind of guilty of this thing that. So they take quantum theory in an almost apologetic way. So something like, we were very happy with classical physics, and now, we're stuck with this thing that it's spooky, it's weird, we don't understand it, and they really try to mold it back into a classical theory. And I think this is maybe what Vlatko was trying to say is not so productive when teaching it, because it's a bit like as if we try to get, to teach Einstein's equations by trying to fit them back into the mold of Minkowski flat spacetime.
Yes.
And this would, probably just defeat the purpose. And somehow we're not doing that with general relativity, but with quantum theory, we are a bit guilty of this way of explaining it to young students, and this creates lots of confusion, because trying to fit a quantum theory within a classical one isn't good and produces all sorts of warped, distorted
yes.
reality kind of effects, which confuse people. Instead, if you just take quantum theory and you take it seriously, as David Deutsch sometimes says, you kind of, you just take it seriously and it makes sense, actually. And I think this is what maybe the whole of quantum information is about,
yes.
our field.
Maybe that's the main message, that so far as we can tell, it's certainly not inconsistent in any way, quantum mechanics. It gives you a perfectly consistent, in fact, beautiful picture of the universe. However, we know that that's not necessarily the ultimate selector. You know, it may still be wrong, and actually we are kind of hoping that it ends up being wrong and something supersedes it, because, you know, it gives us something more exciting to do. But certainly it's consistent. It should not be understood in terms of classical physics. There is no need to go back to that, really. It should be understood within its own kind of language and and mathematical structure. Yeah.
I think it should. We're doing it backwards. We should be trying to see if we can get relativity and GR and everything to come from the equations of quantum physics. Not trying to quantize classical physics. If the universe is quantum,
that would be amazing. That would be amazing if one could even derive GR from some kind of quantum argument. That's maybe an even more radical suggestion that you have. We have no idea. We don't even know how to quantize this classical version of gravity properly without all sorts of mathematical issues. But actually what you're suggesting would be amazing, in fact. Yes.
It sounds like, I've heard Sean Carroll on his podcast, I think, say you seem to be on the same page, and I've heard him talk a few times. I think currently he's working on a undergraduate level textbook that introduces, as he says, he really wants to introduce entanglement right away. And I'm curious if you've had conversations together, or if you're...
Yes, I think I think Chiara had a nice podcast, right?
Yes,
with Sean Carroll. Sean Carroll has this view that, which actually, I'm not sure even who is the first person to suggest that. Somehow Lev Weidman comes to mind, maybe, that the only thing that exists out there is this wave function. You know, that you have the wave function of the universe, and somehow everything comes out of that. But to me, that's very difficult to see how this could be done. I think it's a very nice suggestion. It's kind of appealing, but it's very difficult to put into practice. But certainly we do talk to him. I think we've had interactions with him.
If it was easy, everybody would do
the
it.
common point is just the fact that we think that kind of, quantum theory can be universally applicable.
Yes, we share that
opinion. One thing that we have in common, for sure. Yeah.
Yes.
So I have a question regarding the propagation of the information, the speed of the propagation of information. I did hear you mention Lieb-Robinson bound. I need to check it out. But I mean, from my, if you can expand on that a little bit, because from what I'm thinking is the limitation of the speed of propagation, if you have a bound, adding to some kind of a symmetry, say basically group theoretic requirement. Then you get the relativity, right? The special relativity, and
yes.
So in terms of so I'm just thinking you're talking about non-relativistic effect, and still observing the bound on the speed of propagation. How does that work? If you resort to the Lieb Robinson bound, then I'll check it out. But if you can,
yes, I think we can explain it. Yes, it's a good point. Actually, we can explain it better. It goes back to actually something that probably a friend of mine called Sugato Bose started a while back in quantum information, which was the following question, very simple one actually. You have a spin chain, so you have a chain, one-dimensional chain of qubits, if you like, spin half systems. and they are somehow coupled to each other. I think what Sugato looked at is the nearest neighbor, some kind of Heisenberg model, or maybe XX icing, something like that, nearest neighbors. And then the question was the following: if I flip the leftmost spin, let's say, from the state up to state down, and let's say the whole spin chain starts in the state up, in one of the two states, then you flip the first spin into the opposite state. The question is, how long will it take now for this flip to propagate down the spin chain and arrive at the other end where it actually flips the rightmost spin now? And what's interesting, in fact, I think incidentally Sugato wasn't really aware of Lieb Robinson at all. No. I think he kind of rediscovered this himself. Lieb and Robinson, I think, is from the 60s, maybe even, result. Sugato did this maybe 2002, something like that. I think so the question was really, if I, you can put this more generally, if I make some kind of action that's localized in one part of this system, how quickly will that have an effect on a distant part of the system? You can do it in 2D or any dimension, of course.
Given a Hamiltonian that has a finite range interaction.
That's the key. The Hamiltonian has a finite range interaction, and the energy of this coupling is a finite number. Of course, if you tell me that they couple with an infinite amount of energy, then yes, you will travel at an infinite speed. But the key here is to take this realistic assumption of the finite coupling energy. And then I think you can derive, and that's kind of Lieb Robinson, a very general result, you can derive an upper bound, in fact. It's not exact. They don't give it it's a bound.
It can't be faster than something.
It can't be faster than something. And it's really remarkable, as Chiara said, that it comes out of completely non-relativistic treatment.
Yeah, so you have to assume things like energy conservation. You have to there are some symmetries of these Hamiltonians that you can use in the derivation, and then the formalism that you use is just this. Of course, this bound will be a function of certain commutators that characterize the observables of these subsystems on the chain.
Yes.
And now,
of course, and now, of course, you can say, what happens if I take a chain of coupled harmonic oscillators? Why is this more interesting? Because you're going slowly in the direction of a field. And if this chain of harmonic oscillators, if the distance between the oscillators gets smaller and smaller and smaller, you will end up in the continuum limit. And then, of course, you will reproduce behavior of a field. And that's, of course, known. If you disturb a field in one region of space, then how quickly will this propagate to another region? And so somehow, this Lieb Robinson is a more general way of talking about it, which includes, I would say, the special relativistic side of things. You can describe the electromagnetic field this way as well. But the interesting thing is that it applies to non-relativistic systems.
So, so the action, the energy, the Hamiltonian has to, is that an integral over time? Let's say if I have an Ising model, I don't know if that's an appropriate model to...
Yes.
Okay. So let's say one-dimensional Ising model. And then... so I'm just trying to think... interaction is just immediate neighbor.
That's it.
And... So, but then... How do you get the time into it? I can see that there's steps in it propagating over, but it seems that I can make it arbitrarily fast. How does the time get into that? If you make
the energy arbitrarily high, then yes, you can make. Remember, when spins couple to one another, there is a coupling strength in that Hamiltonian. And that coupling, that coupling actually, I mean, of course, everything is quantum, as we said, and even this coupling strength is to do with Pauli exclusion principle if you're talking about a real magnetic system. So if these neighboring systems are close to one another, then the spins, because if they spatially overlap to a high degree, then the spins have to anti-symmetrize. I'm kind of explaining how a Heisenberg spin chain really arises. And so your Hamiltonian now is really this exchange Hamiltonian, that if you flip one spin down, then the other one must flip up to basically counter. This is like a quantum force. And then this propagates down the chain. As you flip the first one, the next one has to adjust, and then the one next to it, and so on. And that's how this propagates down the chain. But the speed at which it propagates is given by this coupling strength in this case, and that really depends on the details of your physical system. But no matter what it is, it's going to be some finite number.
But the thing that I'm confused here is that, like you say, everything is quantum mechanical, but then everything is also relativistic. So, I mean, it has to be true that if you come up with a theory, then you should arrive at some finite speed of propagation, because otherwise, you will be wrong, right? So
yes, ultimately, you're right. Ultimately, if you write down a Hamiltonian which predicts that you can propagate at the speed that's, let's say, 10 times the speed of light, then we would know that this cannot happen in our universe. You're quite right. So this is more like an imaginary scenario, which only conforms to quantum mechanics, but ignores relativity, really. It's a non-relativistic case. But the interesting point is that
it's even local.
Yeah, even then it's local, and it gives you a finite speed of propagation. Of course, if you add the full symmetry required by relativity, then obviously you end up with quantum field theory. There is much less freedom then.
Sorry, maybe I can ask a little bit more details, because as I remember, basically the Ising model, as you say, there's the coupling strength, but in that the usual statistical model of Hamiltonian doesn't involve time. So I understand that it does. But
it's a dynamic.
Okay,
I think you are maybe confusing it with when you talk about phase transitions and statistical mechanics. This is not statistical mechanics. It's the same model, but you're looking at dynamics. So basically, your Hamiltonian has a set of eigenstates, and when you flip the spin, you're going to create a non-eigenstate. It's going to become a superposition of eigenstates, which isn't stationary, and that's what evolves in time. That's mathematically the way to think about it. But physically,
so basically,
physically what you're doing is propagating a kink that you introduced in the state of the system by flipping one of the spins.
Yeah. Okay. I see what you're saying. Basically, you put in the Schrödinger equation.
That's it. Schrödinger equation.
Yeah.
That's it.
That's it. Yeah. Okay.
It's very beautiful, actually. It's called quantum state transfer. If you want to have a look at
that's it. It's a very instructive calculation that almost exists in one of Feynman's, maybe volume 3 on quantum mechanics. He's got a calculation with spin waves that I think is very similar to this. It's very instructive to go through it.
Sure. Yeah. Okay. I see what you're saying. Yeah. The right hand side, H on the right hand side, and then get the
That's
T.
it.
Yeah.
That's
okay.
it. That's it.
Fine. Yeah.
Hello, Vlatko.
Hi.
You said that quantum mechanics is local, and I do agree with we're starting from everything being quantum, living in a quantum universe, and then tending into a special case to give the classical universe. I 100% agree with that. But the problem I'm seeing here is, you just mentioned that if you try to look at the speed of propagation of a spin chain, like there is the possibilities that the velocity that you get is going to be more than the speed of light.
Yes.
And if the velocity is greater than the speed of light, then that means that the courier of the information allows information to be carried to a past event. So doesn't that makes it feel like, or seems like, there is non-local interaction?
Yes, so this is precisely because this is now all based on non-relativistic physics. So in fact, in practice, this would not be possible, of course, because we know that nothing can really travel, no disturbance, if you like, can travel faster than the speed of light. So you're right. So this, in fact, is another way of showing that non-relativistic quantum mechanics is ultimately inadequate. So you're right. Yeah, this should not be allowed.
Okay.
But I think the point here is not that non-relativistic mechanics is sufficient. It's not. The point is that even non-relativistic one obeys this principle of locality that Chiara was emphasizing. But remember, locality really means different subsystems are in fact even defined. Maybe that's the right way to say. How do you even know that something is a subsystem separated from the rest? The reason you know is because you can do something to it that has no effect on anything else. You know, how do I know that I have 2 qubits sitting in my laboratory? Well, I know that because I can shine laser on one of them and change the state of one of them, while at the same time the other qubit would not change at all. And this actually is a generic property of subsystems in quantum mechanics. As soon as you say 2 subsystems, what that means is that you can affect one of them without changing anything at all on the other one. And quantum field theory, of course, inherits this description then as well. Sorry, Chiara.
I just want to say
unless
ultimately you can state this principle of locality in terms of impossibilities. So the impossibility of changing properties of other systems by acting locally on one system. That's all there is to it. And it's a very general notion of locality, which is implied by the locality in general relativity, but is weaker, is more general and broader. And it's general relativity has that locality, but there are other theories that are not general relativistic or special relativistic that are also local in that sense. And one of them is non-relativistic quantum mechanics.
Yes.
Unless you destroy it, Vlatko, destroy one of them, what happens then to the other one? It's James, by the way. Hi, everyone.
Hi, sorry, destroy which one? Could you
said
repeat
you
that
had
again?
2 particles together.
Oh, yes.
And you said if you change one, the other one didn't affect the other one. But what if you destroyed it?
A great question, James. Great question. It's a great question. I'll tell you why. Because yes, this is what happens when we kind of try to discuss at this intuitive level. It's a good point. When we say different subsystems, they don't have to be particles, and that's the interesting thing. So in this case, what you are talking about is really you should be thinking of different modes. In this, probably a mode would be a different location in space, if you like. So now, creating and annihilating particles is simply like a qubit that exists within this mode, spatial mode. So your different subsystems are now volumes, if you like, of space. And what you're doing is you can, within that volume of space, you can either have the vacuum state or you can make one particle or a superposition of the 2 and so on. It's a great point. And then to link it to what Chiara was saying is that whatever I do in one volume, even if I create a photon, let's say, in one volume, that should not change the state of another distant volume, basically, which would be another subsystem. So it's very important what you're saying. the ultimate subsystems are really modes, according to field theory, not particles at all.
Okay, thank you. So I'll just listen, and if it's okay, I'll develop some questions as I get along. Thank you. It's great chat, by the way, guys.
Thanks a lot.
Thank you.
Circling back around to the paper, you mentioned that this coupling between the phase of the spin might not be related to the gravitational field, might be related to a different field. I think one of you mentioned that there was a specific field that it could be. Could you expand on what properties that field might have if it were not gravity, and how that might be tested? Thank you.
Oh, that's a difficult one. I think I only meant it as a speculation, in the sense that first of all, you would have to really be able to test what kind of propagation through this field you get. So the property that this field should really have is that it should somehow couple to all particles, fermions and bosons, because that's what we require in our model, that we want to explain the exchange phase of any two particles, really, that we choose to experiment with. So now we know that gravity can explain that, because it's a universal force, and we can write a very simple Hamiltonian down. Your question is trickier, because you're now saying, how would you know if it really is done by gravity or by some other field? Then I'm afraid that you would probably need to test more features of this. You would somehow you would probably have to have a better idea even how this propagation works, what kind of particles are involved in this kind of exchange, and so on. So I don't really have an answer to that. We can't probably tell you more than that.
Thank you very much. I mean, the impression that I get is what you're saying is that any force would have to be coupled to anything with energy. And I suppose
that's it.
That's it. Really is gravity at this
That's
stage.
it. It's an obvious candidate.
Yeah, as far as you know, that's the one we have at the moment. But maybe there are other fields of that kind. We don't know.
Yes, and then your question comes in: how would one discriminate? Actually,
yeah, we don't know at this stage. I think it's a nice question.
Thank you.
Thanks.
Sorry, can I have another little question for you guys? Now, if we're talking gravity, we know it bends light, but at the ratios of what? Now, I'll run something by you in a minute once I got my head straight. But right. So I had an argument with the guy from that James Webb telescope, because he couldn't give me some facts and figures on the bend ratio to mass. And what you just said there was it's energy, not mass, that creates gravity or something like that. So there could be a crossover there. And if so, I've just got. I'll talk to you on the back channel about the guys, but I don't want to make too big a fool of myself here. But I've seen the same things, like mass of a planet or a galaxy bending in a gravitational lensing. I've seen it happen on a micro basis, and I'm just trying to. That's what I'm experimenting with at the moment. I'm trying to actually prove it and get it working regularly. But you were right with whoever said energy. It's spot on. Okay, so it's James. I'm done. So
when you say, are you talking about gravitational micro lensing?
Yes. Yeah.
Okay, that's very interesting. What kind of objects? Is it like a neutron star?
Oh no. Man-sized, let's say, people 6 foot. Yeah, that size. But it's good effect. Interesting.
Yes, I think again, any object in principle should do that, obviously, because anything gravitates. If you like, anything that has energy gravitates. But
it doesn't work with an object.
The question is really the extent, the size of this effect, and and that really is that's why maybe that's why people call microlensing maybe neutron stars, but I haven't heard of anything really smaller that would do that job.
Okay, I'll photograph it. I'll put a picture up in a minute, and
that's great.
Okay.
Thanks.
Right.
That's good. That's nice.
So I have some more questions. So I think I will need to read your paper very carefully to understand exactly what you mean by fully local mechanism, and those what. But suppose in a few years, the experiment can be done, and then suppose they they are not what you expected in the paper, then what are your thoughts on that? What are the directions, and your thoughts on that? Can you say something about that? And also, I have a question for you. Also, outside this paper, so because you have a lot of experience in quantum information theory and things like that. How much do you think the theory of quantum information will play a role in our understanding of gravity, and of being able to unify quantum mechanics with general relativity?
Yeah, that's a great question. I really like it because it kind of goes along with some of my long-term interests. I think that one interesting thing about quantum information is that because it's about the information theoretic structure of quantum theory, it really goes at the heart of what quantum theory is and forgets about all the irrelevant details. So when you talk about things like entanglement and quantum superpositions and quantum coherence, etc., you really are extracting the essence, the very essence of quantum theory. And for this reason, I think it's, according to me, very likely that this structure, this deeper structure that quantum information landed on, is the very thing that will be retained once we get to this next theory of quantum gravity. Maybe other features of quantum theory will disappear because maybe the aspects of the formalism won't be there, but what I like to call the counterfactual features of quantum theory that are captured precisely by this concept that I mentioned earlier, like entanglement, locally inaccessible information, and quantum superpositions and so on. All of these things will be there. And that's because they are part of this more robust, deeper structure, which is like a hidden symmetry that's in there in quantum theory, which you can see once you look at quantum theory through the lenses of quantum information. And I think in that sense, all of the pioneers of quantum information made us a huge favor in finding it and developing it, because now we are in much better position, in my view, to think of the next theory of physics.
Yes, and I think it links to your first question, actually, which was about our experiment with superposed masses. What if it failed? This would be a very interesting thing. Actually, it would be much more interesting if it really led to entanglement, as we are predicting, because that I think would be the obvious thing this should do. If it didn't reproduce that, and if we were certain that there were no other influences, that would really suggest that gravity somehow is not quantum mechanical. Now, in what way it's not quantum mechanical would be far from obvious, actually. There would be, then one would have to think really, because, there is even an option, of course, that you produce even more entanglement. You don't have to become classical in this experiment. You can become super quantum.
Yeah.
It's even, for me, as I speak, I find it hard to even imagine how this would be, because we know quantumly what the maximum entanglement would entail. But it could give you something different. And then the question is really that we would have to think very hard how to formulate this new theory. I think the quick answer at present stage is we really wouldn't have a clue what to do. And that's why it would be hugely exciting. I'm almost hoping for that.
Yes. So the answer is definitely quantum gravity is not quantum mechanical, and there's no way to modify your argument or anything to like to fix the theory, like to patch the theory a little bit to like to come up with new an other explanation, or it has to so the answer has to be definitely that gravity is not quantum mechanical.
Yes, although, like I said, that could mean a number of different things in a way. It could indeed be classical, in a sense that it would lead to some kind of collapse of quantum superpositions. And, people like Roger Penrose are fond of these ideas. But having said that, we don't actually have a model for that either. We don't have a consistent picture of even how that would work. We would really need a new principle, even in that direction. But more interestingly than that, I think many of us would not really bet on that possibility. However, it could be different to quantum. It doesn't have to be classical. It could really give us a different result. And then I think we really don't know. It's completely an uncharted territory, I would say. Then we would have to think of more detailed experiments, what to measure, really to go into more details of this, because our experiment is really very general.
Okay, thank you. Yeah, very exciting.
Yeah, thank you.
Yeah, thanks.
Yeah, thanks everyone. That's very interesting questions. So I will just do a mic check to Case, Daniel, and also Frank, Hayward, if you have any questions.
Can I just quickly say something? Ask some questions? It's James again, sorry.
Yep.
Okay, now I've just changed my profile picture. You might need to PTR for it or pull to refresh. I'll just a little example here. Like if you click on my profile picture and make it a little bit bigger, you'll see a white dot in the shadow in the middle there. Now, that's just a little example of what I'm up to, and that's a gravitational lensing. It's pulled the light. There's no light in the foreground behind me. And it doesn't work with a fixed object, and it doesn't work with something static. It has to have energy. So it's more to do with static and the voltage and the frequency that's getting it round the person, okay? That's just a little example of it. Yeah, I'll let you guys know as I go along with the other things. Okay. I'm finished.
Okay, thanks a lot, yeah.
Any questions?
Go Rocket. With regards to your experiment regarding bending space-time or bending light with a mass or energy, I think I'm from a school of thought that mass and energy are equivalent. So are you regards to your picture, are you saying the mass of the object that you're expecting to bend light is an average human being's mass?
I'm saying it's a lot. We're all producing quite a lot of power, static, electricity, and other things, resonant frequencies. And I don't want to say too much because obviously it's my IP at the moment. But yeah, you get in there. I'm just putting you in the right direction a little bit, and just open your minds a little. Rather than with this kind of physics, we've got to open our minds, and common sense isn't going to cut it either, is it? So. I'm just throwing this on the table. I've been playing with quantum entanglement as well as, and right. Has anyone heard of the single electron theory? I know it's probably not correct, but it's just a way of thinking about it. And how things travel faster than the speed of light. It's like the connection's always there, but the power that you need to send, or the power when it's called, that takes a little while to get there, and that's the limiting factor with speed. I'm playing with light spectrum's whole thing really, and it's definitely a human. Well, you can see that it's quite a lot of lensing for just a mass of a person. I don't believe it's mass anymore. Otherwise, I think it's something else, and we just haven't got the lens to see it yet. Hence, they built the Hadron Collider, guys, and I've done some work on that as well. If you have a look at my, I put a link earlier to some of the other stuff I've been doing. Anyway, I've said enough, but I'm not educated in this. I'm an I pilot by trade and that sort of thing. So, but I've got.
So okay, so I want to say something. So are you saying that you're looking at the nanoscale or microscale the bending of light? So because I'm trying to understand, why you no longer think it's energy or mass that's responsible for that, and that's understandable also from a quantum perspective. But there is a famous equation which everyone knows by Einstein, E equals mc squared, and then you're saying, and then looking at that and the Einstein space-time curvature, you're saying that you don't think that the mass or energy, mass is responsible for the bending of space-time, because Einstein make an argument that energy equals to mass. So I'm trying to understand, why you're currently in this line.
Okay, I will do a quick room reset. That's a good question, but maybe a little bit off topic. So today we are honored to have Professor Vlatko and also Professor Chiara here to talk about their research, especially from the room link here. On the top, you will find a recent paper about spin statistics, space-time, and quantum gravity. So for the past 90 minutes, we basically what's the spin and how to understand the spin statistics theorem, and what to look at gravity in the quantum scale, and how the two professors got intuition about this new theory. So we got a lot of different questions. So I will do a quick time check to the professor to see how long you can still stay. Of course, we hope you can, answer more questions, but we also respect your time. And just to check how long you feel you can still be available for us, and look forward to the future discussions too.
Hi, I think we are happy to stay another 15-20 minutes if you're okay with that. And if there are more questions, we are happy to answer them.
Oh, that's awesome. So we definitely have more questions. Got a back channel from the Mo, so please go ahead if you have questions. Thank you.
Hi, thank you. I had a question. I watched Leonard Susskind on quantum videos on YouTube teaching about the uncertainty principle, and I was always confused that the uncertainty is intrinsic because of the act of observing. For example, when we want to see the location of a particle, we have to set a short wavelength, powerful waves to find the exact location of the particle, or we have to use a large wavelength for finding the speed of the particle. I wanted to know that the act of observing is changing, is causing the uncertainty, or it is intrinsic, it's unknowable by nature.
It's a good question. Actually, I think people still view this in a number of different ways. But I would say that it's intrinsic. I think what you're referring to as something that's a property of these states that we use to describe quantum systems. It's not because you really have to observe it, and when you observe it, you disturb it. That incidentally also happens to be true, in the sense that, you know, that's also true classically, of course, to some degree. But quantum mechanically, the states themselves, even when you write the complete information, which is what we call a pure quantum state of your system, so it's the wave function, even at that point you really cannot specify complementary properties to an arbitrary degree of accuracy. And that's what I would say it's basically at the core of the uncertainty principle. So one way, just very quickly, how to really visualize this is that you can prepare an ensemble of particles in exactly the same quantum state. So we have many particles, and they could be completely separated from one another. There is no interaction between them. They're different subsystems. And then you decide to measure, let's say, position on one of them, then momentum on the other, then position, momentum. You go down this chain, you can almost toss a coin and randomly decide which to measure. And then when you completed your measurements, you can then compute the uncertainty, and you will verify that, you know, delta x, delta p is greater than h bar. And basically, what this really tells us is that these quantum states simply are constructed in a way that this information cannot be more accurate than what it is. So, namely, the fact that you measured position on one particle can in no way affect your measurement of the momentum on the next particle in the ensemble. So if you think of it this way, then it's clear that this is not anything to do with the disturbance that you imprint when you measure. That seems to me to be kind of a misleading way to think about uncertainty. So I think the answer is that it's really intrinsic. It's something, probably Chiara would call it like a principle. There's a principle behind that, really, which maybe she would think of in terms of copyability, or not being able to copy these degrees of freedom. But it's a fundamental principle.
Yeah, that's a great question. So maybe I can circle back the paper and ask one question. So it's really intriguing me and make me feel so interested to your research. So still I'm very interested to talk about spin. So in your paper you explain spin as a linear is a consequence of the linearity of the space-time transformation. That's a very new to me. So I'm thinking. So based on my idea. So how do you come from that explanation? Is that because in the general relativity, so there is a tensor to describe the energy matter tensor. So in that way, you think that is the source of the curvature of the space-time. Is that true? Thank you.
So that's one aspect, maybe how you could argue that. Relativity or general relativity and quantum mechanics are different. The quantum mechanics is linear. So if you have two states, then of course a superposition, if you like, is also another quantum state. In GR, this is no longer true. You can have a solution of Einstein equations and another one, and both are equally valid solutions. But if you superpose them, if you do a linear combination, you are not going to be able to get another solution. And in fact, this nonlinearity is the key for us when we talk about, the Mercury perihelion and things like that. This is exactly where this deviates from the kind of conventional Newtonian explanation. So this is true. However, what Chiara and I have been testing with our experiments, all of these, whether in the current paper related to spin or something that we proposed earlier, is all in this linear regime. So I think the first tests would only really be done at that lowest order of approximation, where you could almost think of the gravitational field in the same way that we think of the electromagnetic field. So we haven't got to the next stage of nonlinearity, which I think could also be tested in principle, of course. But in fact, the effect is yet another order of magnitude smaller. So it seems to me that given that what we are proposing is difficult, this would be much more difficult. Even more difficult. So I'm not sure if that answers what you had in mind.
Yeah, I got your point, but I'm thinking how, maybe I should rephrase my question. So how you get the geometry of the space-time correlated to the gravity?
Oh, you mean by correlated? Do you mean entangled?
Yes.
Ah, very good. Excellent question, actually, because that is probably the way to think about our experiment, in the sense that if you make a massive object in a superposition across two different, let's say, spatial locations. And we have two such superpositions. So we have actually 4 different states of these masses. Then each of them would actually correspond to a different geometry according to general relativity. And so effectively what you are thinking when you do this experiment, one way to think about it is that you really have a superposition of 4 different space-times. And then this superposition evolves in some way, and this kind of evolution is what is ultimately reflected in the entanglement that's created between these different masses. So certainly, because gravity is really all about curvature of space-time, well, in this case it would be more appropriate to say curvature of time, I suppose, because what matters really is that time ticks at different rates at different locations in different fields, if you like. So the strength of the field, gravitational field, really reflects itself in how time flows, and so it's more kind of appropriate to think of curvature of time, I would say, than really space-time. But so effectively, each of these elements of the superposition would somehow tick, if you like, at a different rate. The phase would go at a different rate. And these different phases would ultimately then end up creating a maximally entangled state. And if we get that, then what we would be concluding is that certainly some degrees of freedom in the gravitational field are quantum mechanical. If you think of it really in the way that GR thinks about it, then you would really be talking about superpositions of different space-times.
Yeah, it strikes me that, so I think now I get the idea. Yeah, so you describe the experiment rely on the fact that space-time could be superposition, and then you observe some effect, but then you still use the language of general relativity, which, for all we know, is a macroscopic theory. We still don't know if we can use the language of space-time at that level, at the quantum level, yeah. So it's just my comment. Yeah.
Yes, absolutely correct. We don't really know how many of these classical GR features will really survive. So I think usually we like to phrase this in a very conservative fashion, namely that entanglement would show to us that some degrees of freedom in the gravitational field would have to be quantum mechanical. But unless you start writing down models, it's actually even difficult to tell necessarily which degrees of freedom would exactly become quantum mechanical. So I think at the most conservative level, you would say gravity cannot be completely classical and still entangle two objects. But to what degree it is fully quantum mechanical, it's certainly not resolved by this experiment. Then one would have to do more detailed experiments and to show all sorts of other entanglements that would arise from different degrees of freedom and different components of the gravitational field. And in principle, of course, one can test each of these components. It's just in practice, this could be extremely hard because it's a very weak field.
Yes, thanks for the answer to the question. I want to follow up your answer before. So, I understand you the GR theory, and so my question, and also I understand your comment about the theory not complete classical or quantum. My follow up is that so in the Newtonian models, there is a gravitational constant G, and for the general relativity, Einstein also have a Einstein gravitational constant. So that's like a conversion factors to match the units, which is 8 pi G divided by C to the power of 4. My question is, how in your theory or in your model do you have something based on your experiment to quantify the gravitational constant like quantity?
It's a good point. In fact, yes, you could view this experiment as a way of measuring the gravitational constant in some sense. Of course, this depends on all sorts of other assumptions that you make there. Because if you get really, the only thing you are measuring in the experiment is the degree of entanglement between these two masses. And let's say you confirm that they are maximally entangled. You get 1 unit of entanglement there. Then the question is that this is made up of a number of parameters, as you said, which has to do with the masses of these things, the time, the extent of the superposition of each of these objects and so on, gravitational constant and such. So then the question is, they all multiply together to give you this 1 unit of entanglement, if you like. But now if you want to probe them individually, you might need to do this in a different way. Of course, if you could claim that you can independently confirm the time, the spatial extent, and the mass, then indeed this would give you the value of the gravitational constant. So maybe that's one way of thinking about it. But our experiment is completely in the lowest regime, in the Newtonian regime, other than, of course, that it's still a field and it's propagating like a field rather than instantaneous. It's a good point.
Yeah, I see. That's great. I know the William on the stage. Yeah, he was want to ask a question a long time ago.
Go ahead.
Yeah, just a mic check. Will, I'm not sure if you can hear us.
Thank you very much, Professor Vlatko. Milad, I saw you in Singapore near 6 years ago, and you helped me a lot in quantum information, and I'm so glad to see you again. Actually, I have a question. I read your paper, my question is, you consider the mass for superposing. Why are you consider the space-time as a superposition? I mean, we consider the space as a superpose or superposition for a qubit, not the mass. Thanks.
Yes, I think this is an interesting point. This, of course, would be the view if you took on board general relativity fully. That actually, in GR, really gravity, according to GR, you should not think of gravity really as a force, but it's really an effect of the state of space-time, if you like. So there's no other way of talking about gravity, and therefore, if you're talking about different gravitational fields that exist at the same time, ultimately in the GR picture, this really has to be somehow different space-times in a superposition. We don't know if this is the right way to think about it, by the way. It's by no means clear that this is the right quantum picture of GR. It sounds intuitive. It sounds like it should be like that. But I agree with you that we don't know this. There are all sorts of other suggestions where quantizing space and time to some people mean that maybe they become discrete. Things like Planck's distances, Planck's times may become the smallest units in which space-time could even exist or be measured or whatever else. So in fact, we don't really know what the quantization of space-time entails. And when we say that some degrees of gravity should be quantum, we also are not necessarily clear as to which degrees of freedom, unless we can execute all of these experiments, like I said, to really test all the components of the gravitational tensor. I'm not sure if this was clear.
Thanks. Thank you very much.
Thank you. Thanks a lot.
Yes, thanks for the question. So I have another further question. So, how do you plan to do like further experiment for this theory, or like for the proof? Since it's very interesting, I still feel there are a lot to do to, as you just mentioned, to do the nonlinear region of the experiment.
Yeah, I think this is an interesting question actually for the future research. I think it's a nice one to maybe leave this discussion with these kind of thoughts about the future. We are investigating a number of possibilities, in fact. When Chiara and I think about these experiments, we have a range of systems in mind. The other day, we spoke with Mark Kasevich, who does fantastic Bose condensate experiments. He kind of throws the Bose condensate in the air and makes it into a superposition at two different heights, and then looks at the gravitational effect of this and so on. So certainly systems of this kind, of course, what he would have to do is double this and have two condensates each in a superposition for long enough for gravity to matter and so on. So these are possible experiments. We have all sorts of nanomechanical oscillators in mind, things that are very small in size, maybe a nanogram weight, but they are very close to one another and they can vibrate in a quantum mechanical sense. So you create some kind of quantum mechanical vibrational state, and then you wait for long enough that they actually couple gravitationally, which will then affect the state, and hopefully they would get entangled. So here we are talking more like two coupled quantum harmonic oscillators, but coupled through gravity. There are all sorts of other experiments where people are even thinking of, these would be lab-based, but people are even thinking of space going on these small satellites and trying to, one advantage, this would be horrendously difficult, of course, and they would have all sorts of disadvantages there to start with. But one huge advantage is that you could do them in free space. You would eliminate any local variation of gravity, because once you get to these very sensitive level, and the metrology has to be extremely precise. Even I think the experiment that they were doing in Vienna with one of these oscillators was such that I think a bus driving by nearby would actually make a big enough shift that you could detect it in your experiment. So I think, these are hugely sensitive experiments, and I think if you could go in space and eliminate any kind of local imperfections, this would be advantageous. So these are things we are thinking about. Of course, mounting an experiment of this kind on a satellite is itself a huge problem in that case. Chiara and I also thought about neutrinos. We had some crazy ideas to do a double beta decay kind of experiment, but I think this proved to be too insensitive, right? Too small, the effect.
Yes. I think when we talk about, when we wrote that paper with David, we kind of conjectured the existence of some related, similar particles to neutrinos, but more massive, that could lead to some observable phase. And then we also thought of some variants involving a single particle with with the kind of acceleration-related effect, which is the Sagnav effect. So I think you can think of creating entanglement between different degrees of freedom within the same particle, and using a kind of acceleration effect to indirectly show that gravity also has to be quantized.
Yeah.
And that may be easier to realize in some sense, because there's only one particle, but it might be harder for other reasons.
Yes.
And then you had this collaboration with some other people where you were looking into bosons and condensate self-energy and kind of ways of distinguishing some quantum models for that from classical models, which kind of would show us the quantization of gravity in some sense. And I think I'm working with we were working with a student who is also interested in these things, and he's looking into trying to find a witness for like single particles, so we can make it simpler. And the experiment can become a bit more simple compared to the one we have now, which only has two particles. But it's kind of my view that I think we both agree on this, that somehow the entanglement seems to be the strongest argument we have. So it seems to me that we could simplify the experiment to a single particle, but then it might be less convincing.
Yes.
So we would need more assumptions for that.
Certainly entanglement between two objects, and I think ideally it would be great if this happened somehow naturally. If there was something out there in nature already as a phenomenon that leads to this kind of scenario. Alternatively, of course, people are working on engineering this in the lab, but I think it would be amazing if something like an astronomical phenomenon could also lead to something like that. That's why we thought about these kind of neutrinos as maybe something that is already affected by this. But as we said, it unfortunately turned out to be really too small. But it's not to be ruled out that there are larger objects which could be in superposition, and maybe this would affect gravity as well. So we are really considering a multitude of experiments.
Oh, that's awesome. Yeah, I feel like the harmonic oscillator and the telescope you are talking about is very interesting, and especially the single particle entanglement. That's very cool. So if you can demonstrate a state with a single particle on a single photon non-collinearity, that's very cool. So looking forward to
great. Thanks a lot.
This scope. Yeah, thanks so much.
Thanks very much. This was great. We really enjoyed it.
Thank you so much. Yeah, it was great discussing. Thank you.
Yeah, so I just might check to see Frank, Cecile, or anyone else on the stage have questions.
Yeah.
If not, we probably will race back to Vlatko and Chiara's time, and look forward to them to come back.
Great, thanks a lot,
Cecile,
guys.
go
This
ahead.
was amazing.
Yeah, thank you very much.
I just have one
Thank
question.
you.
Thanks for the great sharing and discussion. I joined late and wasn't able to follow in depth of the foregone previous discussions. But just out of general curiosity on the subject of the title, can I think of the attempt of quantizing gravity in a way that similar to the history of quantizing, say, the black body radiation, or you're just borrowing from the quantum mechanics quantization and say gravity is quantized in the similar way? I guess my question is not based on the educated from the previous discussion. Just my layperson type of curiosity, if that's something relevant.
Yes, I think it is relevant, certainly. It's just that at this stage there are many approaches how you would quantize this. And as you say, all of them more or less follow the logic of how quantum mechanics came up in the first place. So basically the question is which kind of degrees of freedom do we really upgrade from numbers in GR to operators, to quantum mechanical things. And our experiment would not really necessarily be able to tell you that. It would tell you that some of them have to be upgraded, and you certainly have to have some complementary degrees of freedom. But I think if you wanted to know exactly the details of that, like I said, we would need probably to do more detailed experiments. But I think the first initial guess is that we would follow very much the logic. You mentioned black body, which actually ended up being the basis not just for quantum mechanics but for quantum field theory. Of course, you can now use the quantized electromagnetic field to treat the black body. And I think in the regime that we have in mind, in the linear regime for gravity, we would very much follow the logic of the electromagnetic field and do it like that in the first instance. And I think that would be sufficient to describe our experiment. But, that wouldn't tell you anything about the remaining degrees of freedom. And I think then that would be very interesting to explore. So we would have a partial answer to that, but certainly not a full answer.
Thank you.
Great, thanks a lot.
Professor Vlatko, I just want to ask you, I haven't read your entire paper, but you a while ago, Chiara had mentioned the Sagnac effect. Were you able to do that experiment based on the Sagnac effect?
Not yet.
Not yet. It's just a proposal. But we are talking to some experimentalists who might be able to realize something like that. But for the moment, it's really just a proposal.
Yeah, because when I read the abstract, I was reminded of somebody from Stanford who came here. He was trying to make an experiment on how to design a quantum computer using an interferometer, and the setup is similar to what is described in the Sagnac effect. So I'm very, very, looking forward to what's going to happen in your other experiments.
Yeah, that's great.
In the future.
Thanks. Yeah, we are also actively talking to various experimental groups. We'd love to see that realized as well. Thank you.
Yeah, also.
Yeah, thanks so much. Go ahead, Cecil. Do you have more to say?
Yeah, I just want to request Professor Vlatko and also Chiara to come back with us. I saw that maybe Chiara is coming up with a book which is very, very interesting, and I know that you have a lot of research papers, and because we wanted to, raise the level of quantum photonics higher and try to relay to papers and talk about hard science in a way that people would really appreciate it more. So we'd like to invite you back in the near future to come back and discuss more of your work and other papers.
Great.
Thank you
I'd
so
love
much.
it as well. Thank you.
Yeah, thank you very much. Yeah, I'd love it. It's very nice to have this space to discuss physics ideas. It's wonderful. Yeah, it would be great. Thank you.
Thanks for inviting us back as well. Thank you.
Yeah, thanks, Vlatko and Chiara. It's a very much pleasure to hear from you, and especially to talk about your great research. So for all the people here, thanks for joining the room today. And also please follow the Professor Vlatko and Chiara's work if you are interested to learning more. So at the top of the room there is the link about Professor Vlatko's research. So you will find more interest in the research they are doing. So if you are interested in collaborating on some idea discussion, please feel free to do so. And we'd like to see, we provide a platform for all the great minds to exchange ideas. So thanks so much for this great discussion. Look forward to have the Professor Vlatko and also Chiara's back again soon. I know it's very late for the Professor Vlatko and Chiara. It's like 11 p.m. At London time. So really appreciate for your dedication and time and consideration and great explanations. So hope you have a good night, and we look forward to see you soon.
Great, thanks a lot. Good night. Yeah, take care.
Everyone.
Thank you.
Thanks for tuning in.
Thank you very much, Vlatko and Chiara.
Thank you.
Bye.
Yeah, thank you, everyone. Thanks everyone for joining this great session. We can plan to do a after party if people are interested in discussion more. It's a very deep question which can lead from lots of different domains. So we'd like to cover more related topics in the future. So if you are interested, please follow Quantum Photonics Club, and we will see you very soon. So I will give the mic to Cecil to announce the future rooms. And we have the Dacel here. Yeah, thanks, Cecil.
Yeah, our next room will be talking in a few hours. We'll be talking. This is a part 2 of women in STEM, women who changed the world. So this is a part 2 because there is a lot of requests that we received to make a part 2 of this room. And tomorrow evening in our usual club time, we will have another physics room, which is going to talk about EUV and UV. That's a new trend. It's about lithography that's being used as a new trend in semiconductors. And on the night after, we will have a discussion about free will ethics and free will. And I just want to tell you that I just got a confirmation from a new research from MIT and some researchers from Sweden. They will be coming back. They will be coming here to talk about geometry and ADS-CFT. So they have a research also related to quantum gravity. So please follow Quantum Photonics. We have not yet set what time it will be, but it might be similar to this time that we have now. So just follow the club to see that the schedules that we will be having in the future. So thank you. So Mike, to you, Chiara.
Yeah, great lineup, and also we have 2 more quantum computing related sessions. One is with IBM quantum engineers to talk about superconducting approach. Another is with Code Quantum, the executive management team. So yeah, they will talk about the cold atom approach and also the general overview about superconducting. So that will happen at the end of March, but the schedule is still under discussion. So feel free to follow Quantum Photonics Club, and we will see you very soon in our future amazing rooms. So thanks much for today's speakers and also all the participants in the room chat. That's really great discussion and great questions. So I will give the mic to Despel. And also special thanks to Cecile, Hansen, Frank, and also our regular friends and fans. Yeah, go ahead, Cecile, if you want to say.
I would just like to also excitedly announce that we're going to have a discussion about Gödel's incompleteness theorem about the halting problem. If you will look at the schedule that we have, you will see it. And there's also a discussion about the lemur transform, which is something new as an alternative to the wavelet.
Hansen, Frank, and also our regular friends and fans. Yeah, go ahead, Cecile, if you want to say.
I would just like to also excitedly announce that we're going to have a discussion about Gödel's incompleteness theorem about the halting problem. If you will look at the schedule that we have, you will see it. And there's also a discussion about the lemur transform, which is something new as an alternative to the wavelet transform and the Fourier transform. And that's going to be exciting because a paper just came out, and please watch out for that, and many more coming. So yeah, we get inspired because of you, so please continue to support us. Thank you. And if you have suggestions or speakers or topics, please just DM us. Thank you so much. Darcel, mic to you.
All right, I will do a short count. I really enjoyed it. This was very exciting. Since we have another room tonight, I'll do a short count, and we're going to start with 5. Is everyone ready?
Ready.
There we go. 5.
5.
4.
4.
33 and a third.
33 and a third.
2. Sierra, Cecile, and Hansen, you are all number 1. Call it out.
Yeah, and Frank, Darcel, and everyone in the room, you are all number 1. Yeah, thanks for joining us. Appreciate it. 1. Yeah, so thanks for the great questions and great engagement, and look forward to see you soon in our future rooms. And have a good day, have a good night, and wherever you are.